Hello everyone, my name is Wan-Hsuan. I'm a PhD student from UCLA advised by Professor Jason Kong. Today I'm happy to present our latest work MLQS multi-level quantum layer synthesis. This is our line for today's talk. I will begin with the introduction about quantum layer synthesis and multi-level framework. Then I will present how we use this framework to solve the layer synthesis problem and provide some future direction. First, let's begin with the definition of quantum layer synthesis problem. The input to this problem is a quantum circuit shown at the above figure. Each horizontal wire represents the program qubit, and the box on the wire indicates the gate. In addition to the circuit, we have a coupling graph. Each vertex in the coupling graph is a physical qubit. Only two adjacent physical qubits can perform a two-qubit gate. In layer synthesis, our goal is to map each program qubit in the circuit to a physical qubit and schedule gate execution time. This shows a valid layer synthesis result. First, we have mapping from program qubit to physical qubit. Then, we have time coordinate to indicate the time to execute the gate. Lastly, we may have some extra swap gate in the circuit to change the mapping to accommodate required connectivity. The objective in layer synthesis problem can be either minimizing the circuit depth or swap count. I will use a concrete example to show why we need swap gates in this case. Based on the previous example, assume we have the following mapping on the device. Based on this mapping, we will execute gate 0 on this physical qubit, and we can derive the physical qubit similarly for gate 1 and gate 2. For gate 3, now it's acting on a pair of adjacent qubits, so we can directly execute it. Then we continue to execute the other gates until gate 10. Under this mapping, gate 10 needs to act on a pair of non-adjacent qubits, so we cannot perform this gate at this point. What do we do? So our solution is to insert the swap gate to change the mapping. After swap gates happen, we exchange the mapping for Q0 and Q1. After that, gate 10 is acting on two adjacent qubits. This is a valid operation now. So that's how we use swap gate to update the mapping to accommodate the circuit connectivity to device connectivity. I would like to review previous work. First, this problem has been proven to be pretty hard. There is a heuristic approach which are quite efficient but suffer from quality degradation when problem size increase. On the other hand, people have proposed several exact approaches. They are often solver-based methods. For example, we have interlinear programming or satisfiability module theory solver. Although they achieve good performance, they have poor scalability. For example, they fail to solve problems with like 10 to 20 qubits. So our first step is to push the scalability of the exact tool. In our DAC 2023 paper, we improved the constraint formulation, encoding, and optimization techniques. It shows thousands of speedup compared to OSC, which is our initial tool for quantum layer synthesis. With this technique, we are able to scale to solve problems involve 30 to 40 qubits, but we still cannot scale to solve problems with 100 qubits, which are the size that current hardware supports. So our second step is to use a hybrid method combining both heuristic and exact method. The key idea is to improve the heuristic method by providing more global optimization information from the exact tool through multi-level framework. In terms of the performance, we demonstrate the effectiveness by having 53% swap reduction compared to the leading heuristic tool Sabre. And then in terms of the scalability, we can solve instances with hundreds of qubits in reasonable runtime. Next, I'm going to show what is a multi-level framework. Here I'm using circuit placement as an example. So initially, we are at the finest level, which is the original problem size. We have a chip and then a circuit. Our goal is to place the cell in the circuit and the chip while minimizing the wire length. At the final level, it's hard to directly solve the problem. Even the optimal tool will demonstrate performance degradation. So the first step in multi-level is to do clustering to generate a hierarchy of problem approximation. The coarser level is the stage where the optimal solver can solve the problem exactly. And at this stage, we will have global optimization information. The runtime overhead is justified by the high quality solution. With that, we will do interpolation to project the solution at the current level to the final level. Since the solution directly derived from them may be invalid and may not be the best one for the current level, we will use efficient tool to do refinement operation to have local optimization around the solution. We will continue to do this process until we reach the final level. This process calls the V-cycle. People can have multiple V-cycle. The advantage of having multiple V-cycle is that when we do the second V-cycle, when we do clustering for the circuit cell, we can consider not only the net connectivity, but also the physical location given by the previous V-cycle. So that gives us a high-quality clustering solution. Next, I'm going to discuss the challenge when we apply multi-level framework to solve quantum layer synthesis problem. Here we are beginning with a Quaco circuit which can have zero swap solution on the Riccati-Aspen architecture. Here I show the connectivity graph required by the circuit. Based on the circuit, we will do the following clustering. Intuitively, the program qubit clustering will made based on the number of 2 qubit gates acting on the qubit. We will tend to cluster qubits that have a lot of 2 qubit gates acting on them because after they become a coarser qubit, they will stay with each other during the compilation. So this is the coarser circuit clustering. We will have this new connectivity graph required by this circuit. For the device, we have different options. For example, here we can have different device topology if we make different clustering choice. The first challenge here is that how do we decide the size of a cluster? What happens if we have a cluster larger than 2? The issue is there will be some hidden cost within a cluster because when we cluster program qubit together, the gates acting on the qubit within a cluster, we cannot observe that at a coarser level. So if the device side, we don't have a cluster with actual connectivity, then when we do declustering, we will have significant cost increase. So to ensure that we have accurate cost estimation, our solution is to keep the compression rates equal to 2 to ensure liberal cost execution within a cluster. The second challenge is the difficulty in device clustering. Because distinct topology between final and coarser graph defines the different solution space due to the change of relative qubit distance. So our solution. So let's first take a look at what happens if we go ahead and solve at the coarser levels result. The first option gives us a solution with 4 swap, while the second option gives us a solution without any swap. Why is that? It's because the second option has similar connectivity as the one that required by the circuit. So in that case, we propose the idea of circuit-informed clustering, which is very similar to the better clustering given by the second V-cycle. So here's how we do clustering. We base on the existing layer synthesis solution. The right-hand side shows the device, and then the index are the program qubit index. First, we generate a coarser program qubit. We compute the affinity between qubits based on the number of 2 qubit gates. We will iteratively cluster 2 qubits that has the highest affinity between them. And the second condition is they map to adjacent physical qubit. So for example, we will cluster qubit 6 and 7, then 12 for 15. For 0 and 1, since they are not mapped to adjacent physical qubit, we won't cluster them in this case. Instead, we will continue and cluster the next entry in the list, which is 0 and 5. For the physical qubit cluster, we will generate that based on the program qubit clustering. For example, if 2 program qubit is clustered, Then its corresponding physical qubit that they map to will be from a Corsa physical qubit as well. So that's how we generate the Corsa devices that are similar to the circuit clustering. The next challenge is the discrete solution space. This makes us unable to do interpolation because we are not able to directly derive a valid solution for final level based on the Corsa level result. And it's difficult to predict how optimization will propagate across level. To overcome this, our solution is to do refinement operation based on the concept of qubit region. So first, we use Q2 as an example. At the Corsa level, it belongs to Corsa qubit 6. And in the option 1, the Corsa qubit 6 is mapped to the following region indicated by blue. So this will be the region where we expect that Q2 should stay within at the final level. However, at the Corsa level, we may make some mistakes, so we also include a neighboring green region for Q2 to explore. When refinement operations solve within this region, we achieve the following result. Surprisingly, option 2 still gives us a swap-free solution, which confirms that the circuit info clustering is quite effective. So here is our overall flow. We will begin with a heuristic tool as refined. It can provide high-quality QoS as the guidance for clustering, and it also serves as an effective refinement operation at each final level. And we use TB-OSC2 to do Corsa level solving. In S-Refine, we have simulated Newlin-based initial mapping, and we use A*-based swap insertion to do the routing. Here is the evaluation result. Compared with Sabre, we have 57% swap reduction on the non-optimal benchmark. For the general circuit, we have 45% swap reduction compared to Sabre, and the scalability is quite good. It takes 10 minutes to solve a problem on average. Finally, it's a takeaway. We propose MLQoS, which is the first work applying multi-level framework to solve the problem in quantum computing. More importantly, this framework is quite flexible. We can plug in any exact tool for Corsa level solving and use other tool as refinement operation. Thank you for listening. This is the QR code for our paper and GitHub. Feel free to read our paper and try our tool. Thank you.